All right, let's dive into the incredible world of digital signal processing, or DSP. This is the hidden magic that powers, well, pretty much everything. Our digital audio, our images, our communication systems. It's all about turning the smooth, analog world we live in into a stream of numbers a computer can actually work with.
But that right there brings up a really fundamental problem, a question we have to answer. How do you take the perfect, infinite, beautiful world of mathematics, the kind of stuff you see in textbooks, and make it actually run inside the very finite, very practical world of a computer? It's a way bigger challenge than you might think. And the source material just hits the nail on the head here. Some of the most foundational tools in signal processing theory, things like the Z-transform or the discrete time Fourier transform, well, from a practical point of view, a computer just can't handle them directly. They're not built for that kind of math. Yeah, you've really got these two completely different worlds. On one side, you have this elegant theory that's built for signals that go on forever and frequencies that can be any value you can imagine. And on the other side, you've got the hard reality of a computer, which can only handle a limited, finite number of data points and can only do one calculation at a time. They're fundamentally at odds. So, how in the world do we build a bridge across that massive gap? Well, it turns out the solution is a truly brilliant computational tool, one that was designed for this exact problem. And here is the hero of our story, the discrete Fourier transform, or DFT. You can think of it as the practical, gets-the-job-done cousin of those other theoretical transforms. It is specifically designed to analyze a finite little chunk of a signal, which makes it the perfect bridge between the world of pure theory and what a computer can actually do. Now this is what's so amazing. You take an entire field of frequency analysis, the power to look inside a signal and see all the hidden frequencies that make it up, and it all gets boiled down to one simple, elegant three-letter command. That is the whole goal of applied DSP. Okay, let's look at another core DSP operation, convolution. It's how we apply filters to signals. And if you were to do this by hand, oh man, it's this whole complicated process. You have to take one signal and fold it, then you have to shift it, then you multiply it by the other signal, and then you sum up all the results. And all of that is just to get one single point of your final output. And this right here, this perfectly illustrates the whole point of modern DSP tools. It's all about taking that complex, really intensive procedure and packaging it up into an efficient, practical command so that engineers and scientists can build amazing things without getting totally lost in the weeds of the math. So, okay, we've got these incredible tools that can analyze frequencies and perform these complex operations. What can we actually build with them? Well, one of the most common and most powerful applications is creating what we call digital filters. At the very heart of most digital filters, you'll find something called a difference equation. Just think of it like a super simple recipe. All it does is tell the computer, hey, to create the next piece of the output signal, just take a little bit of the last output you made and add it to the new input you just got. It's a really simple step-by-step recipe that can completely transform a signal, one sample at a time. And you guessed it, we see the same pattern again. A core concept in signal processing, taking this fundamental recipe for a filter and bringing it to life, is made totally accessible through a single, powerful command. This is what lets people design and test incredibly complex systems with amazing speed and ease. But this digital world, this whole process of translating perfect theory into practical code, it isn't flawless. There's a hidden cost. There's a subtle price we have to pay for converting that infinitely detailed analog world into a finite set of numbers. Just think about it for a second. Your computer can't store a number with infinite precision, right? It only has a limited number of bits. So every single calculation, every single time it represents a real-world value, it has to do a tiny bit of approximation, a little rounding. So what are the consequences when those tiny little errors happen millions or even billions of times a second? Well, that unavoidable error has a name: quantization error. You can think of it like a faint static, a constant, low-level noise that gets baked into our signal. It's a ghost in the machine that engineers always have to be aware of and design their systems to handle. And this noise, it's sneaky. It doesn't just come from one place. It creeps in at every single stage of the process. Right from the initial moment you convert the analog signal to digital, to every single multiplication the filter performs, and even in how the filter's own settings are stored in memory. So really, the critical point is that a huge part of DSP engineering is just managing this trade-off. The goal is always to keep the power of the signal you actually care about way, way higher than the power of this unavoidable digital noise that you're just forced to live with. It's a constant balancing act. Okay, so we've talked about these fixed filters built from static equations. But the next frontier in DSP, well, it's a lot smarter. What if we could build filters that could actually learn and think for themselves? And that brings us to the next evolution, the adaptive filter. This thing is not static. It doesn't just blindly follow one recipe. Instead, it actively looks at its own output, figures out how well it's doing, and then modifies itself in real time to get a better result. It literally learns on the job. And these smart filters, they're absolutely everywhere. They're the reason your phone calls are so clear. They cancel out the echo. They're what helps improve the pictures you take. They suppress noise in all sorts of devices. And they are absolutely essential for making sure your high-speed internet connection stays stable and fast.
Now, the engine driving a lot of these incredible systems is the LMS, or least mean squares algorithm. It's this really elegant and, importantly, computationally simple process that uses the filter's own mistakes, the difference between what it wanted to do and what it actually did, to guide itself toward a better solution. It learns from its errors. But even here, on this advanced frontier, it's all about trade-offs. The LMS algorithm is wonderfully simple to compute, which is great. But as the source points out, the price you pay for that simplicity is that it can be kind of slow to adapt. And this just reveals a core truth of all digital engineering. Our entire modern world is built on a series of really clever mathematical compromises.
So, if you take one thing away, let it be this. DSP isn't just about abstract math. It's a story of practical ingenuity. It is the art of the compromise, of taking the perfect, sometimes impossible, mathematics from textbooks and forging it into the efficient, powerful tools that make our digital world not just possible, but actually work.
And that leaves us with a final thought to chew on. These tools, the ones for filtering and adapting, they're the fundamental building blocks. But they're not just for cleaning up signals anymore. They're laying the groundwork for a future where our systems can truly interpret and understand the world around them through sound and images and all sorts of data. What's that future going to look like?